Thank you. Okay, well, good to see you. We were talking about Gaussian naive Bayes and logistic regression last time. I want to continue a little bit that discussion. We had an interesting discussion after class a little bit as we were talking about things like what are the decision surfaces, how would you actually do gradient descent for logistic regression and things like that. As you probably noticed, your new homework assignment gives you a chance to implement logistic regression with gradient descent. So I thought it might be worth spending a little bit of time directly on that. So that's where I'd like to pick up. So as we were saying before, we brought up Gaussian naive Bayes as one way of dealing with training a classifier if we had continuous valued exabytes instead of discrete valued. We were talking after class that, of course, there are many, many different probability distributions that are appropriate for real valued variables. Gaussian distribution is just one of them. And it actually assigns a non-zero probability from minus infinity up to plus infinity. So, for example, if you had a continuous variable like weight, the weight of a person, you might notice that's always non-negative. Your weight can never be negative. And so, it might be interesting or useful to pick a different kind of probability distribution than Gaussian in that case. So, for example, a Poisson distribution would be an example of a different distribution that could assign probabilities to real valued numbers. But despite all that, it turns out it's very common for people to use Gaussian naive Bayes if they're going to implement naive Bayes for continuous valued variables. Despite the fact that you can sometimes do better by picking a different distribution, and there's nothing wrong with doing that, it often turns out that the violation of modeling assumptions that's introduced as soon as you assume everything is conditionally independent is has more impact anyway than the specific distribution you use to estimate to characterize the probability of each exabyte. And so for that reason, sometimes people just go ahead and use Gaussian anyway. But you should at least be aware that, of course, we could use other kinds of distributions. There's nothing magic about Gaussian. And we talked about how to estimate the parameters. One thing we didn't talk about, but I think is interesting, is to think about this. Suppose that we are training a Gaussian naive Bayes classifier, and we have some problem where it's perfectly correct to model that problem as a Gaussian naive Bayes classifier. And in fact, just to make the world simple, suppose that I have just one exabyte. It's called x sub 1. And I have two classes. Let's see. I'll just call them class 1 and class 2, and suppose they're y equals 0, y equals 1. And suppose they're equal priors. They're both 50% probable. Then one thing that's kind of interesting to think about is what I'm going to estimate, of course, are these terms. And if this is 0.5 for both y equals 0 and y equals 1, then I can draw here my probability of x sub 1 given y. Here I can draw the naive Bayes classifier in a way we can think about it, look at it. So for example, of course I'm going to have what it means to estimate this is that I'm going to have a probability of x1 given that y equals 0, and then another one for the probability distribution given that y equals 1. And so let's just pick some here. Suppose here's the probability. That's an artist's conception of a Gaussian distribution. And let's say that's this one, the one for y equals 0. And maybe here's the one for y equals 1. I don't know why I get those funny horizontal lines. There it is. Okay, so maybe here's the Gaussian distribution for on x sub 1 in the case where y equals 1. So this would be a typical kind of situation. So now if we, and suppose we've estimated these from our training data. Let's assume they have the same sigma. We make that assumption that we're estimating the same sigma for each class. And you can see they have different means, different mu's. Then if I give a new example to classify, you can see that if I give an example over here, it's obviously going to have higher probability of being generated from the distribution, from this distribution, than it is from that one. And so I'll end up labeling it y equals 0. If I pick one, say here, it's going to have obviously a higher probability of having been generated from this distribution than this one. So of course I'll label that one, this example, y equals 1. And you can see that the decision surface is basically everything to the right of this point is going to be called y equals 1. Everything to the left will be called y equals 0. So we could think this is the decision surface. I have to modify my decision surface. Okay, but you get the idea. So everything over here, we're going to say y equals 0. Everything over here, we're going to end up saying y equals 1. And so in this simple one-dimensional illustration, we have a linear threshold, and everything over there will be more probable to have y equals 1. And, the further we go there, the even more probable it will be that y equals 1 compared to y equals 0. But one thing that this diagram makes clear is that if we're training a Gaussian naive Bayes classifier, and it's the correct model for our world that we're trying to train for, then we never can actually achieve 0 error. There's a kind of unavoidable error here. That is, if for example, suppose our classification task is to predict who's a football player. Yes or no, that's y. And this x sub 1 is the weight of the football player. Then we might say, well, in our training data, people who are football players tend to be heavier than people who aren't football players. But there's some distribution, some Gaussian distribution. There will be some lighter weight football players and some heavier weight non-football players. And so there's actually this inescapable error. And in fact, if we ask what is that error, we could even solve for it. It's basically the probability that we're going to get a particular, any randomly drawn example wrong is the probability that we'll draw an example that was actually generated by this distribution, but is over on this side of our threshold. So that'd be like the integral, if we happen to generate, there's this much probability mass that will generate a person who's a football player who's lighter than our threshold. Plus there's some other probability mass that will encounter a non-football player whose weight is greater than the threshold. Right? So really the unavoidable error, we're going to error here is just then going to be the integral from minus infinity up to, let's call this threshold t, up to t, of the probability that of x, of encountering the value x, given that y equals 1, dx, right? Plus this other region here, which is just the integral from t up to plus infinity of the probability that x, that will encounter that x given that y is actually 0, dx, right? So, see what I mean? How did that happen, man? Okay, you see what I mean? That was not a trick. Okay, now you see what I mean. So, this is just kind of a good thing to keep in mind, that when we're talking about these kind of probabilistic models, that in many cases the model itself doesn't even assume that we'll be able to get perfect classification accuracy. Okay, so what I want to do now is just do the two-dimensional version of that plot. And again, suppose, let's do it this way. I could play football, but I guess I pre-did this slide so that it's play basketball. And my two variables in this case are height and machine learning grade. And you might realize that it's more likely if people are basketball players, they're probably going to be taller than most other people. And if they're serious basketball players and they don't do their homework very much, then it probably will also influence their machine learning grade. So we could now plot it this way. Here will be my x1, which is height, and here's my x2, which is machine learning grade, and now my y values are 0 and 1. Do they or don't they play basketball? And just like before, I could, let's sketch out what a Gaussian distribution might look like for, say, y equals for y equals 0 and for y equals 1. Right, so these might be the distributions of heights for basketball players and non-basketball players. And similarly, there might be, let's say, lower grades for basketball players. And somewhat higher grades for non-basketball players who have more time to study. Okay. And so now, of course, when I get a new example, I want P of y given x1 and x2, which, according to our naive Bayes rule, is just going to depend on the product of these different P sub i's, right? So I'm going to multiply. If I have a new x, some point on this plane, a new x to classify, I'm going to classify it according to our usual naive Bayes rule, taking the prior into account. Let's assume half of our examples are basketball players just to make the prior unimportant to us. But then we're going to multiply together the probabilities of these. And so where on this plane will it be which x would I choose that would make it most probable x given that y equals, say, 0? Okay, you're being shy today. Obviously, it's going to be this value for x1, and it's going to be this value for x2, right? So if I want to know the most So it's sort of, that point would be where the product of the probability of x1 given that y equals 0 will be maximum here, and for x2 it'll be maximum there, and so their product will be maximum, obviously. And similarly, for y equals 1, it'll be kind of over here, like there. And if these variances are all the same, let's assume they are just to make my picture easier to draw, then you could imagine that if I drew a contour map coming out of the screen here, showing the probability of x sub 1 comma x sub 2 given y equals 0, then that contour map would be a hill where the peak of the hill would be coming straight out from there, right? And then, because it's a Gaussian distribution, we might find something like this for the contour map. And so forth, right? So that's just a two-dimensional Gaussian. But we would get it if we actually multiply these Gaussians together. We'll get another two-dimensional multivariate Gaussian. And similarly, that's the Gaussian we'll get. That's basically, this Gaussian is the probability of x1 and x2 given y equals 0. And then similarly, I could draw the other Gaussian that I'll get for the probability of x1 and x2 given that y equals 1. That would look more like this. And so forth. Okay, and so now, just as in the one-dimensional case, the decision surface now will be where there's equal probability of observing that x given that y equals 1, and that should be equal to the probability where y equals 0, because that would be sort of the decision surface between which would separate our examples, so our labeled examples. So it would be, if I had drawn this correctly, this will be a straight line. Ha ha ha. Pretty straight line. Okay, but you see, this is our decision surface. So on this side is this whole region where it's more probable that y was 1 given we observe these x's. On the other side of that region is, we're going to label it y equals 0. At least this will be a line in the case where, as we proved last time in class, where we assume the sigmas are the same for y equals 1 and for y equals 0. And so there's our linear decision surface, which we proved last time we'd have. So this is another one of the pictures that I kind of carry around in my head. It's not as messy as the written version of it. It looks a little bit scary this way. But you see, it's just a way of realizing that, number one, what do we mean when we say we're making this conditional independence assumption? All we mean is that we're modeling the joint probability of a particular x1, x2 given y as the product of two individual Gaussian distributions. And furthermore, if you think of those as surfaces coming out of the screen, then you can easily see that given our classification rule, the decision surface is going to be the set of x positions where the probability of x1, x2 given y equals 1 is exactly equal to the set y, the probability of that given y is 0. Okay. Now, we were talking about this after class last time, but if we don't assume that the sigmas are the same for y equals 0 and y equals 1, then, in fact, that nice linear decision surface won't necessarily be linear anymore. So we could have, if I had, even in one dimension you can kind of see this, but for example, suppose here's my distribution for x given y equals 1, and here's my other distribution for x given y equals 0, then, man, it's going to be messy. But, here's the way I've drawn this. Here's one point that's about equally probable in the two distributions. Here's a second point. Here's the third point. So I might end up getting, say, a parabola like this. Right? So you can get all kinds of nonlinear things. In fact, even if you just think of the simple one-dimensional case, can anybody give me an example where it's not even linear in one dimension? Yes?
The same mean, but then you have a much smaller standard deviation for one Gaussian than the other, then you have
yes.
a search interval where like the one opposite of it.
Great. So that's the right answer. I'll draw it rather than repeating what you say. But in fact, they don't even need to have the same mean. They could, but you're suggesting here's one distribution. It's very peaked. That's a Gaussian. Here's another Gaussian. And so now, what's my decision surface if the point is here? Suppose this is my y equals 1 Gaussian, and here's my y equals 0 Gaussian, and this is my x. So if x appears here, we're going to label it y equals 1. In fact, if x appears in this interval, we're going to call it y equals 1. But over here, we're going to call it y equals 0. It's more probable to be generated by a y equals 0 if it's there. And similarly, over here, we're going to call it y equals 0. So it's not even a single threshold anymore. And you can imagine what that looks like in two dimensions, too. You have little circles, little pools of y equal 1 separated by oceans of y equals 0 and things like that. Okay, so it can be, in general, Gaussian naive Bayes, the important thing is in general, Gaussian naive Bayes can give us very nonlinear decision surfaces. Even though we did make that nice little assumption that the sigmas that we're estimating for each x sub I and each value of y, if we happen to assume that those don't actually depend on y, then it turns out that it's going to be linear. And when we derived our logistic regression formula, the form of p of y given x that's used by logistic regression, we did make that assumption that the sigmas were independent of the y value. And so this is just kind of a reminder that even though there's this beautiful thing where we can show, well, look, the logistic regression form of p of y given x is exactly what we get if we start with Gaussian naive Bayes and assume those sigmas are independent of y. And then we get a nice linear decision surface, and logistic regression is the right way to model it. I just want you to keep in mind that in general, if we don't make that simplifying assumption about sigma, then we can get very nonlinear situations. Okay? Okay. So then we talked about logistic regression, and we talked about how we would extend it to the case of multiple values of y, not just two. And I used this slide last time. it occurred to me that I should today tell you about a second way that you can do this, which is going to be very widespread in the upcoming neural network homework assignment. So this is indeed one way we could handle the case where, let's say y could take on the value 1, 2, or 3. Then for, if y can take on r values, then for all of them except 1, we can model p of y given x in this form. And for the last one, we can get away with this without introducing any more new parameters for the rth y. And why can we do that? The usual reason is because the probability of all of these given the same x, they have to sum to 1. Y has to have some value for any given x. And so that's why in this last one we don't actually introduce any parameters for the class y equals r. We only have r minus 1 sets of parameters. And then we rely on the fact that since they're going to sum to 1, we can actually get away with this. But a very common thing to do is to just go ahead and give a set of parameters also for the rth value of y. It's a little less efficient in terms of number of parameters that we're estimating to capture the distribution, but it's nevertheless common, and it gives us a form which we call the softmax function. And now it just looks like this, very simple. We say it's the same thing, we have r different values of y, and now what we do is for each one of those values, the k value gets its own set of parameters. And this is actually, if you decide you're going to use a set of parameters for each value of y, then this is actually the form you'll get if you redo our whole derivation. And then it comes out this way. So this is actually not very different, say, from what we had before. We had these linear sums raised to some, raising e to some power, and then the denominator here was just the normalization thing that made sure that all these things sum to 1. And what we're doing, if we do the softmax version, is basically the same, except that now we don't have that constant 1 in there anymore. But you can easily see that if you add up all of these for the r possible classes, then they do sum to 1 because that's what the denominator is. Okay? But this will turn out to be a very widely used form, and so this is sort of worth being aware of, and we'll talk more about it next lecture. Okay, but I wanted to cover that. Okay, so now on to actually doing gradient descent for logistic regression, the thing which is in the current homework. So here's just our summary of what we talked about last time. We're going to do maximum conditional likelihood estimate. That is, we want to find the value of our parameter vector, which maximizes over the observed training data. Here we're taking the product over all of the different training examples. That's what the L index is, the Lth example. We just want for every training example to have the observed y be the most probable. We want to choose the w's that make the observed y's the most probable given the observed x's. And since we assume all our training examples are independent, we just take the product. And so if we want to derive our gradient descent rule to do this, we basically just go back to the same strategy we used when we introduced maximum likelihood estimates, which is let's write out an expression for that likelihood. Here's one version of it. We could put it in terms of, we could substitute these terms in for this, but get an expression for that conditional likelihood, and then take the derivative and set it to 0, or somehow optimize it. And so here's what that looks like. The log of that likelihood looks like this. We saw this last time. And as I pointed out, we have to do gradient ascent or descent to get this to work. In this case, I'm taking the log of we want to maximize the conditional likelihood. So in this case, we would do gradient ascent, or if we took the negative of that, we do gradient descent, as we talked about. But we didn't get last time to what is this gradient? Right, so here, E is actually the function we're trying to optimize. That's our log likelihood. But we need to figure out what is the derivative of the, if we want to do descent, negative log likelihood with respect to each of these parameters in our logistic function. We need to figure out what those derivatives are. Uh-huh.
So the second form of the previous in the formulation that we use all the exponential W instead of y minus 1. But when we do the optimization for that problem, we get the generic solution to the problem.
Oh, very good question. So the question is, if we use the softmax kind of framing of logistic regression, do we get a degenerate solution because now we've kind of used more parameters than we needed to express? The answer is actually no. It turns out, pretty sure it's still a concave function. And so gradient descent will still get us a unique, well, yeah, I think it still gives us a unique solution. So I may need to think about that a little more carefully offline, but I like the question. The question is great. I'm pretty sure the answer is there's no issue there. We just end up estimating bigger parameter vector than we need, but it's still, the solution is still unique. Cool. Okay, so we talked about doing gradient descent last time, but we didn't get to what is that derivative? And it turns out, again, you can work this out and you can look at the reading to get the exact derivation, but here's our log likelihood, and if we take the derivative of that log likelihood with respect to any given W sub I in our logistic function, this is in the case where y could be 0 or 1, it's just Boolean, then here's what that gradient ends up being. And look at what this means. It's actually very intuitive. What we're saying is, if we want to increase the log likelihood of our data, the change in y that we want to make, the gradient, the partial derivative, is this. It's the sum over all of our training examples of the value of that example, which is, of course, is going to be either 0 or, oh no, x is continuous, sorry. It's the sum over our examples of the continuous x sub I value times this quantity. Now, y can be either 0 or 1, of course. And if y is, let's say, 1, then this quantity is simply the amount of misassigned probability mass. Right? If y is actually 1 in our observed ELF training example, and currently our logistic function predicts that the probability of seeing a 1 was 0.9, then we have a misassigned probability of mass of 1 minus 0.9. But if our probability was only 0.5, we have a bigger misassigned probability mass, and the derivative with respect to that weight will be even higher. And remember, in gradient descent, what we're going to do on each iteration of gradient descent is add some constant times this partial derivative. That's what the gradient is. The gradient is simply the vector of all those partial derivatives. And we're going to update our weight by adding that vector to our current weights times some learning rate. And so it does make nice common sense that the bigger the misassigned probability mass, the bigger the derivative, and the bigger the the bigger change we want to make to WI. Y could be, of course, 1 or 0. We just talked about the case where y equals 1. In the case where y equals 0, then, of course, this just becomes minus the probability that y equals 1. And so in this case, basically the amount, in the case where the observed label was 0, what we're doing is we're measuring the error in terms of how much probability mass was misassigned to the y equals 0 case. Well, that's the amount that's assigned to the y equal 1 probability. So you can see this gradient is actually this wonderful common sense thing that just says basically when you update your weights, move them more or less in the direction that will reduce this error. And the bigger the error, the bigger the misassigned probability mass, the bigger change you should make to the weight. And we do that simultaneously, of course, to every weight in the logistic function. So when you implement it, it's actually this simple to calculate. And notice that this quantity here is just the output of the logistic function itself. That's what the logistic function is. It's the probability that y equals 1. So in terms of implementing it, it's simply a matter of subtracting the output of your current logistic function from the observed value and multiplying by the magnitude of x sub I. Okay, so again, you'll get plenty of opportunity to look at this in more detail in the homework, but that leads to a very simple algorithm for gradient descent for logistic regression, which guaranteeably optimizes makes the maximum conditional likelihood estimate for our weights. That is, chooses the weights that make the observed data the most probable it can be. And the gradient descent rule simply says, on every step, update each one of your weights where the ith weight gets replaced by its old value plus this delta which you add in based on the derivative. Okay? Comments, questions? Okay. So this is pretty nice, and it's pretty straightforward if you look at it through this lens. Okay, so now, since we're on a roll of talking about maximum likelihood estimates, the obvious question is, what about a map estimate? What if we have some prior knowledge about our weight values that we want to introduce? And that would be a very natural reason to use a map estimate if we have prior knowledge. In fact, a very common reason to do it is if we believe in Occam's razor, if we believe that simple logistic functions are more likely to be right than complex logistic functions, that is, we want the weights to be closer to 0. We a priori think that most weights are more probably small than large. Then we can capture that by putting a prior on, which is the probability that a weight will take on a particular value could be some function like this. And actually, I should draw it this way. A common thing is to do this so that right here where the weight equals 0, I hate when this happens. Okay, it came back. Right here where the weight is 0, we could make that most probable a priori. What's going on? I may have to... Just trust me. That's where W is 0. Okay, so we can put that kind of prior on, and if we do, then we can get our map estimate, which of course, just as before, means that we want the most probable parameter set, W, given our observed Y, and because we're doing conditional likelihood here, also given X. Bayes' rule tells us how to write that. And and of course, the denominator there, P of Y, X's, doesn't even mention W, so we can ignore the denominator. Now, if we also assume that the weights and our observed data, our observed X's, are not related, which is a pretty reasonable assumption, then we can write that joint distribution as just the product of 2. And now again, we notice that P of X is independent of W, so we can just ignore it. If we're trying to maximize W, or maximize this with respect to W, we can ignore that final term. And we're left with this, which, if we now decide we're going to maximize the log of it, the log of the product becomes the sum of the logs. And now recall that we're putting in a prior, for example, that says we a priori think our weights are following a Gaussian distribution with 0 mean. It's most probable that the weight will be 0, but it's not somewhat less probable that they'll be far from 0. And so if we put that in, we end up with this. Because when we take the natural log of this big thing, we end up with the natural log of this, which doesn't really depend on W, so we can ignore it, plus the natural log of this, which is just that term. Okay, and this is our old term, the data likelihood, which we already dealt with in the maximum likelihood case. And so you see what's happening when we go for a map estimate with assuming a prior of 0 mean Gaussian distribution on our weights, is we're putting effectively a penalty term. The bigger WI gets, the bigger penalty we pay. In fact, it goes as the square of the size of WI. And so as we try to maximize this entire expression, what we're doing is we're trading off choosing a W that maximizes the correctly assigned probability mass for our predicted Y's. But we trade that off against the size of these weights. And so this is sometimes called a regularization term. But the idea is that it's something that follows our prior, and this particular prior turns out to be a good one for reducing overfitting. Because it does capture Occam's razor, which despite my philosophical issues, in fact does work in practice. So, okay, so that's what the map estimate ends up looking like. And if we work it out all the way to the level of a gradient descent update, here's our old one that we saw for the case of maximum conditional likelihood. Here's the corresponding expression that we get for gradient update if instead we go for a map estimate. And you see the only difference is that now we have this term which says basically update your weight by moving it closer to 0. If your weight is negative, you're going to subtract out a negative number and move it closer to 0. If the weight is positive, these two constants are positive, by the way. So if the weight is positive, then you're going to subtract out some fraction of that weight to move it closer to 0. If the weight's negative, you're going to add in a quantity which moves it closer to 0. So this term on every gradient update step moves the weight a little bit closer to 0 compared to what you would do if you didn't have that prior. And again, intuitively, this makes perfect sense, right? It's exactly what you want to do if your prior was that the weight should be small. You'd want to make it close to 0, and so if on each iteration you do that, in addition to what you were going to do before, it makes perfect sense. So whenever you're in the situation of deriving these mathematical things, it's always good to look at the final result like this and just see if it makes common sense to you. And in the case of logistic regression, it's one reason I'm going through the details of this is it really does make sense. And you can kind of see that the math is doing for you the thing that your intuition tells you should be done. So. Okay, so any questions on this? All right, then let's move on to one more point. So we've talked now about getting map estimates using a zero mean Gaussian prior. That's very frequent. It's one of the two frequent kinds of map estimates that we use for logistic regression and many other gradient methods that we use, many other learning algorithms that we use gradient descent for. There's a second very common method, which is instead of using a Gaussian prior, use, oops, oh, I see what I'm sorry. We'll get to this. But the second method is to use a Laplace prior, which gives us a slightly different term. And I'm sorry, I thought that was the next slide, but it's not. So we'll get to that later on. Okay, but the bottom line is this. For logistic regression, it's just of this form. And we can use gradient descent to train it. In your homework, you'll get a chance to show that not only is this the form we'll get if we assume that the x sub i's are real valued and we use a Gaussian naive Bayes classifier, but you get the exact same form if you have Boolean valued x sub i's and use our original naive Bayes classifier as the starting point for asking the question, what's the form of y given x? So you'll get a chance in the homework to show that for yourself. Okay, so I want to spend a few minutes on basically the question of when would you use logistic regression and when would you use Gaussian naive Bayes, and who cares, why are we learning both of these algorithms? And in fact, you can think of naive Bayes and logistic regression as exemplars of two broad classes of learning algorithms that are based on manipulating probabilities. They're often called generative and discriminative classifiers. In this case, naive Bayes is the generative classifier, and logistic regression is the discriminative one. But the idea is that generative classifiers estimate the parameters for both p of x given y and p of x, and then use Bayes' rule to calculate the probability of the label given the observed x's. Whereas the discriminative classifiers, including logistic regression, just directly estimate p of y given x. And one reason these are called generative, the first one, is that think about the following thing. Suppose that I've trained both of these on the same data. And now I'm interested in, let's say, this quantity. I want the joint distribution on x and y. So if you've trained your naive Bayes classifier, can you calculate the joint distribution on x, y? Can you calculate this? Sure, because we know just from the basic rules of probability that that's just this quantity. And those are exactly the two things you're estimating from naive Bayes. So yes, obviously you can. What about for logistic regression? See, you can't do it. In order to calculate the joint distribution from this, you can't really do it. You need to also know P of x. Then you can multiply P of y given x times P of x and get it. But you don't have P of x. In fact, that was what we advertised as a feature of logistic regression, that we weren't going to waste parameters estimating P of x because we don't need it. We get the x's, and we're just interested in P of y given x. So that's one way to think about the difference between one of the key differences between naive Bayes and logistic regression is that naive Bayes really is estimating the entire joint distribution in these two terms that it's estimating, whereas logistic regression really isn't. So that's a difference. Okay, so which one would we like to use? And the answer is a little bit subtle. It depends on really two questions. One is, how restrictive are those modeling assumptions that are being made? And the second is, how much data do we need to estimate the parameters of the two? And do those parameter estimates converge more quickly in the number of training examples for one of those classifiers than the other? And so the answer is kind of a blend of the answers to these two questions. So let's first think about the modeling assumptions. One way to think about it is how many parameters I need, right? So I think you already know the answer to this, but I'll ask you again anyway. If I have, let's say xi are continuous, y is Boolean, and I have n x sub i's, then how many parameters do I need for my Gaussian naive Bayes? Right, exactly. 1 plus 4n. But we'll never be back. 1 plus 4n, right? So we need 1 for P of y, the prior on y, and then for each of our x sub i's, we need the mu and the sigma, given that y equals 1, and the mu and the sigma, given that y equals 0. For logistic regression, well, here's the answer. We just need n. There are only n w's here. Oh, n plus 1. Right? The 1 is this w0. Why do we need that w0, by the way? I mean, it did fall out of the derivation that we did. But one way to think about it is, as we said before, this gives us a linear decision surface in the Euclidean space that x lives in. If we didn't have this w0, then that linear decision surface would have to go through the origin all the time. And so this lets us build linear decision surfaces that don't have to go through the origin. And we have this basically because we have the prior on y. Okay, so one thing we might think is, well, there's a different number of parameters here. Maybe this will converge more quickly because it has fewer. If we plot how well our estimates, how accurate our estimates are versus the number of training examples, maybe we'll do better here because we have fewer parameters than that. We might also think, well, this might be more expressive because it has more parameters. And as we just saw earlier, Gaussian naive Bayes can build nonlinear decision surfaces, whereas logistic regression can only do linear ones. So you see, so it is a little complex. But it turns out that, in fact, counterintuitively, even though naive Bayes has more parameters to estimate, if you look at the expected quality of those estimates, the expected error, or the variance in those estimates, as you grow the number of training examples, it turns out that these actually converge more quickly than these do as you grow the number of training examples. And at an intuitive level, the reason is that the naive Bayes parameters that we're estimating, those mu's and sigmas, we're estimating each of those parameters independent of the other parameters. If you want to know the mean for x sub 3 given that y equals 0, you just get all the examples for which that's the case and you find the mean, and that's your estimate. It doesn't matter what those other parameter values are. But in the case of logistic regression, it actually does, because one way to think about it is if you take that linear form, W0 plus the sum over I of Wi xi, then if I wiggle one of those parameters, the gradient descent method is going to want to wiggle the others to make up for it. So those parameter estimates are coupled in the sense that the value of Wi depends on the value that you're estimating for Wj. And so that turns out to matter a lot in terms of the convergence rates. To be a little bit more precise, here's an interesting result. So here's what we can say formally. Let's let epsilon sub an refer to the expected error. When I say expected, I mean if we do a random draw of n training examples, it's the expected value over those different random draws of training examples. But let epsilon an refer to the expected error for learning algorithm A after it sees n training examples. And let d be the number of features for which we're estimating our naive Bayes or logistic regression parameters. Then here's what happens to be the case. The estimate after n examples differs from the asymptotic estimate as we go to an infinite number of examples. This error will be less than the error we would get if we had an infinite number of examples by this much, by some term which is on the order of square root of d, the number of features, over n, the number of examples. Whereas for Gaussian naive Bayes, it's on the order of the square root of log of d over n examples. And again, this is essentially because the Gaussian naive Bayes estimates are all independent. And so one way to think about that is if we say want these terms to be equal, then obviously log d is going to be better than d. Or put another way, to get this to be a 1, I need number of examples n to be equal to d, whereas here I only need a number of examples equal to log d. So in that sense, Gaussian naive Bayes converges in expectation more quickly as you grow the number of training examples to the accurate estimates of its parameters more quickly than logistic regression does. Okay. And in fact, this paper by Andrew Ng and Mike Jordan, they also did some experiments. They took a bunch of training data sets and they plotted naive Bayes and logistic regression in the error rates as a function of the number of training examples for a whole bunch of different data sets. And you can see that in practice, theory is not perfectly followed every time, but it is followed on average. So for example, if you look at this first one, this is logistic regression. This one is naive Bayes. And so what you see is that in the early going, when you have only a small number of examples, naive Bayes actually achieves a smaller error than logistic regression. But then as you grow more and more examples, logistic regression outperforms naive Bayes. That's the empirical. It's not true in every case. Maybe it would be true, maybe it wouldn't if we had more examples, who knows. But when they cross, it's usually in that form. Logistic regression losing in the sparse training data scenario, and then winning if you have more data.
So the previous slide is that of the greater than or equal than. So here, when we have finite number of training example, the error should be larger.
Here, when we have what?
The epsilon like LR on n with finite example should be larger level than the.
Yeah, so this means this error will be less than the asymptotic error plus a quantity that grows as square root of d of n. Right? So this will actually be presumably bigger than this term, but less than this. So this is telling us sort of this is capturing the variance in the estimate as a function of n, but in a way that we can directly compare the two. Okay, so to me, the bottom line here is that the situation is complicated. If you want to know whether you want to use logistic regression or naive Bayes, think of it this way. Logistic regression is trapped in this situation where it can only express linear decision surfaces. Gaussian naive Bayes, if we make that simplifying assumption about sigma, is trapped in the same difficulty. But if we relax that simplifying assumption and let it estimate independent sigmas for each term that it needs, then it can get nonlinear decision surfaces. So in that sense, Gaussian naive Bayes can be more expressive than logistic regression. On the other hand, there's a sense in which that's also not, there's a sense in which logistic regression is more expressive than naive Bayes, which is this. Think about that conditional independence assumption. When you train your naive Bayes classifier, and when you then later use it to classify a new example, you're making use of that conditional independence assumption. Right? When we went to classify a new person, whether they live in Squirrel Hill, we again, at classification time, made the conditional independence assumption. We just multiplied together each of the probabilities that are x sub I is given y. But in logistic regression, nothing about the training procedure, gradient descent, is buying into conditional independence. And nothing about the classification either. The only place where we made use of conditional independence assumption when we discussed logistic regression was in defending why we chose this particular functional form for p of y given x. So the conditional independence assumption for logistic regression, we only mentioned it to justify the form that we're going to use for p of y given x. And that was a commitment of sorts. But then the training algorithm is free to just find the best linear decision surface, whether or not it corresponds to some conditional independence assumption. And so the net effect is that logistic regression can learn pretty much any linear decision surface, whatever gradient descent tells it is going to maximize the data likelihood. Whereas the linear decision surfaces you can get from naive Bayes are more restricted. They have to correspond to, well, when we did that derivation, we actually came up with an equation for how to calculate W sub I from the various mu's and sigmas that we were estimating. And so you can't actually get every linear decision surface in that way. Whereas logistic regression, since it's using gradient descent, can learn any decision surface, any linear decision surface. So there's a sense in which Naive Bayes is more expressive because it can build nonlinear surfaces, but if we force it to use that simplifying assumption about sigma and therefore get linear surfaces, they will be fewer possible linear surfaces for that version of naive Bayes than there is for logistic regression. So, as I mentioned, the story is a little complicated, but that's effectively what's going on. So there's a difference in how expressive they are. There's a difference in the training procedure and whether or not it actually pays attention to the conditional independence assumption. And then there's a difference in the convergence rate of their parameter estimates toward the truth as a function of the amount of training data you have. So it's complicated, but it's interesting and kind of important to just be aware of these kind of different considerations, because that's what influences really our choice of learning algorithm when we confront a new case. And so in your summer job where the Chinese restaurant hires you to decide who to send their advertisements to, be sure at the beginning of the summer you ask them how much data they have, a little or a lot, because it's going to influence what kind of classifier you decide to. Okay, any questions on this? Yes? The question is, should we use an ensemble, just combine both methods? I've not seen that done, but that doesn't mean it's a bad idea. I've never seen it done. I don't know. Good question. If you had a summer job, that might be a good way to spend it. Okay, so there's one more type of regression that I want to talk about. It's actually just called regression instead of logistic regression. It's very widely used. It's basically to handle the case where y is continuous, and so our x's might be continuous or discrete or some combination of those. And for example, if we want to predict a stock price, that's a continuous variable. It's not discrete. And so there's a family of methods which go by the name regression methods. The thing that I want to do here is talk very briefly about linear regression, partly because it gives us a chance to look at one more case study of what's now becoming a very familiar template for designing learning algorithms, which is we look at the type of data we're working with, we choose some functional form, we make up a probabilistic model to go along with that, and then we solve for the maximum likelihood or the maximum a posteriori probability parameter estimates, depending on which principle we want to follow. And regression we can use to illustrate the same kind of example. We can do the same thing. So let's look at this very simple example of regression. Suppose I have just one variable x and I'm trying to predict y from it. And suppose, furthermore, I decide that, at least in this picture, f is going to be a linear function. Y is going to be some linear function of x. And suppose I get a set of training examples like this. This might be, say, number of hours doing homework and midterm score, for example. If we want to proceed with our probabilistic approach, then we want to start by asking, how can we take this problem of fitting this training data with a linear surface and frame it as a maximum likelihood problem? And this slide actually shows the answer to that. That's the typical answer, typical justification for regression. And here's what it says. It says, y is actually, we assume it's some deterministic linear function of x, or some deterministic function of x. In this picture, it happens to be linear, but it wouldn't have to be. But we assume that the y examples are generated probabilistically, given an x, by first calculating the true value of y, and then adding in some noise, which is indicated by epsilon. And then we observe the true value plus some noise. Furthermore, typical assumption is that that noise comes from some Gaussian distribution, n means Gaussian, whose mean is 0 and has some variance, sigma. Okay, so this is a model that says, well, the probability then of observing a particular y given an x is just going to be some Gaussian distribution whose most probable value is whatever f of x really is. But there's going to be some variance here in the value we actually observed, which is due to this random zero mean Gaussian noise being added to it. Okay. And as we know, the expected value for any Gaussian distribution is just the mean of that distribution. If you draw a lot of samples from a Gaussian, the expected value is the mean. And so the expected value for y is actually really just f of x. And so that's our probabilistic model. You can think of it as as generating y given an x by first calculating the correct value of y and then generating a random noise and adding that in. And so that makes y a random variable because it's the sum of a deterministic value plus a random variable. Okay? So it's not the only way you could model noise in data, but it's a reasonable way. You might have some measurement, some sensor noise in the sensor that's measuring the value of y. Of course, not if y was your midterm grade, since we score those perfectly. But if y was instead, I don't know, how many grams of fat are in the ice cream based on the store. Okay, so it turns out this model is going to lead us to a very simple formula for getting maximum likelihood estimates and map estimates. So let's see how that works. If we assume this is linear regression, just to spell this out a little bit more, then we assume that the mean, the real f of x, is of this form. It's just some linear function of x. And so p of y given x is just, as we were saying, a Gaussian where the mean is, depending on x, that. And that notation we've already seen. So now if we want to train, here's what we can do. We can say, if we want to choose the w that is maximizing the conditional likelihood of y given x, just as we did in logistic regression, then what we want to do is we want to pick the w's parameters that maximize, just as in logistic regression, over the ELF training examples, the probability of the observed y given the x's and the w's. And as before, we can turn that into maximizing the log of that. And in this case, of course, we know the form of p of y given x because we just said it's going to be whatever f of x is plus some zero mean Gaussian noise, or a Gaussian distribution whose mean is actually f of x, whatever f of x is. Okay, so there's how we can now frame this in the familiar form of a maximum conditional likelihood estimate. And now we can just solve for it the same way we did everything else. In fact, we can do a gradient descent algorithm for solving linear regression By doing what? What would we have to do next? We have to start by writing out the expression for the likelihood, and then getting the derivatives of that likelihood with respect to each of the parameters that we're trying to estimate, which are W0 and W1, our linear function f that we're trying to learn. Okay, so that's not too hard, it turns out. It turns out, let's see, it turns out to actually be pretty straightforward. And here's the answer. It turns out that the W's that are going to maximize the conditional likelihood are just the W's that minimize the sum of the squared errors in all the predictions of the function. As for each training example, we want W's so that when we sum over the training examples, the difference between the predicted y and the observed y, the square of that difference is minimized. Some people just call this sum of squared errors, and that's typically what people optimize when they do linear regression or many other kinds of regression. And it turns out to follow directly from this, and you can see it right here. In fact, if I decide I want to maximize this quantity, which is just the product over L of all these terms. And now if I decide maximizing that is the same as maximizing its log, then when I take the log of this, it's some term here, the log of that, whatever that is, plus the log of this second thing, which is minus 1/2. So you can see this follows directly from that. So maximizing this is the same as minimizing, that's where there's a negative sign here. Minimizing this sum of squared errors. It's kind of analogous to that logistic regression rule that said we want to minimize the misassigned probability mass. Well, here too, it's just that because it's a Gaussian distribution that ends up being the exponential term in the definition of the Gaussian. But many times you'll take when I took an engineering course on regression many moons ago, the course began by saying, oh, many people minimize the sum of squared errors when they do regression. And then we went forward from there. But here you can actually see that it's based on exactly the same kind of principles as we've been using for deriving the other learning algorithms. In fact, it's just under some probabilistic model where which is a reasonable one about zero mean Gaussian noise, then minimizing the sum of squared errors is equivalent to maximizing conditional likelihood. Okay, so that's all we're actually going to say about linear regression in the course. You can see if you look forward in the slides, I give the derivation of the gradient descent rule if you want to do that. But what we're going to do next time is start in on neural networks, and you'll see that we train them using exactly these same principles. So in some cases, we'll be training neural networks to minimize the sum of squared errors of their predictions. In other cases, training them to optimize the misassigned probability mass when we want to interpret those neural nets as expressing probability distributions. So all this kind of background stuff is really a scaffolding we'll continue to build on as we do neural nets. Okay.